Start. There's the clock. So, welcome to another exciting computer architecture class. I guess we're getting ready for our break, which is also very exciting. And because after you guys all leave, it'll be pure remote and nobody will be coming back. So, just going to run through a few dates with you. I've got my calendar here. It looks to me like you're going to be on recess until the 30th, which means we're not back for another, well, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 days. So you got a 10-day break, 10-day weekend. And that's pretty good, 10-day weekend. Back on the 30th, resuming online classes only. And then the last day of classes is the 11th. And then finals week begins on the 15th. So we have to have a final. And I'm thinking that our final will be on the 17th. So I'm just going to write down final for CR346 because that's the old number that I remember. And for those of you who are also in the microcontrollers class, that's EE346, or I don't know what the new number is anymore. I think it's 3,346, which makes it sound better.
Will the final be like an online exam, like on Blackboard, like the format of the homeworks?
Absolutely. Yeah, we're not going to be able to meet in person for the final. So it's going to be open book, open notes, and I'll do a mashup of our prior homeworks and come up with a final that, well, essentially we'll have to give you 2 weeks to do it. So finals will have to be assigned on the 3rd. If we're going to have them done on the 17th. So I'll make a note of that. So we'll assign final in CR346 and EE346. And so what that means is that we'll still have the 7th and the 10th, and perhaps even the 3rd, to go over the final. And let's see, last day of class is the 11th. And so after the Thanksgiving break, the semester ends incredibly fast. I mean, just not mind-numbingly fast. And so that's that. Now tonight, I think we have homework 10 is due. Today is the 19th, so yeah, homework 10 is due tonight. Homework 10 is due. And you also have a homework 11. Now, homework 11 is due on the 3rd. So homework 11 is due on the 3rd. And I'm just jotting this down. You might like to as well. And that'll give you plenty of time. We'll have one last day on the 30th to answer questions about homework 11. But I'll try and answer most of your questions for you now. And I can see that people have already made some attempts. So perhaps that's a good sign. People are on their way to finishing homework 11. So that's that. Any questions about the dates? I guess it's a little bit unusual for everyone because it's kind of getting up there in the numbers with the COVID. You know, we're up to almost 600 infected on campus, according to the dashboard, which is like a lot. So I'm staying far away from campus. I'm ordering my books from the library to be delivered. Everything's pure online for me from now on until you guys come back. And I guess that's not until February, right? So you're coming back a little bit later too. So that's something. So let me see what I can do to answer any questions you might have about homework 10. That's due tonight. Any leftover questions from that? No. Hearing none. I shall move on to homework 11, which is on systems. Maybe we started going through this already. So perhaps the thing to do, I'm not exactly sure. Does anybody remember what question we left off with last time? I think it was up there in the teens.
I think it was 11. I'm not sure though.
11. All right, let's get up to 10 here. And I think we covered the direct media interface. It's an interesting thing that goes on here with the it's the compare and contrast, right? I was going through this process before when we were trying to examine the M1 from Apple. When you look at parallel architectures, and I'm just going to quickly allude to this diagram here. This is your typical NUMA architecture. This is the non-uniform memory access. And what you've got over in here is your slots. These are like your DIMM slots. And then the multiple channels. And what you do with the quad banding through a memory controller is you use relatively lower performance RAM, but you make your accesses distribute. So you access from here, then there, then there, then there. And by the time you get back to here, the data is presented and guaranteed to be valid. And so you interleave your queries. And this CPU is tightly wound and tightly tied to these slots. These memory slots are geographically co-located. Then somewhere across the motherboard, there's another CPU with a whole bunch of more slots. And Xenon architectures are classically done this way by Intel. And that CPU and memory controller has access, tight access. And so you might have something like 75 cycles for access time to the DIMMs out in these slots. But if you wanted to go to the DIMMs from this CPU into the DIMMs in those slots, according to the specs, you get like 120, maybe 140 cycles of access time. And so because you have to go through the intermediate CPU to get to these slots, there's a substantial expense. And so that's why they call these non-uniform memory axes or NUMAs. And so when you think about, what's going on here, you basically have a slow link and a substantial distance, and the speed of light being such that it is, plus the extra slow link that you have to go through, has a substantial overhead associated with it. Now, as it happens, the two CPUs could theoretically share some high-level cache, let's say L3 cache, but have to their own self an L1 and an L2 cache. But in fact, what we see from like the fabric that Apple has in its M1 is a different approach. It's a more uniform memory architecture because everything goes through the fabric, and there isn't a slow side of the memory and a fast side. Everybody goes through the fabric to gain access to the shared memory, and then the shared memory is allocated by pages using the translation look-aside buffers, and they are residing inside of the memory controllers. So therein lies the compare and contrast. You look at the big Xenon boards, and these are the kinds of things you could expect in a server room, like over at AWS and Amazon Web Services. And then you have to do an allocation, and you have to decide how many CPUs you want. And sometimes if you distribute like a database across multiple CPUs where the memory is shared across slots from different CPUs, things will actually get slower. And that's a problem. So like this physical CPU 0 could actually be 4 cores with an L3 cache. And they could all be regarded as symmetric, multi-threaded, and they're all able to like make this big bulky chip. But there's another big bulky chip in all of this, and so they're both working on the same motherboard. And there's, certainly it's fast to access the slot on the left from the CPU on the right, but nowhere near as fast as to access these locally positioned slots. And so that's what we're dealing with when we're dealing with non-uniform memory architectures. And people who are trying to figure out the best way to do it usually have to dynamically benchmark, and not just once, but over a long period of time. And that's in order for them to achieve some kind of computational consistency, because in some cases things will run slower and some things will run faster, and you don't really know how anything is going to run until you try it. And there's no predicting it. And if you're doing an allocation of a computer on the cloud where you have multiple CPUs in a chip, and then you have multiple chips on a board, you've got to figure this stuff out. I mean, that's profiling. You profile the code. So that's that. Let's take a look now at the at what we have here. So this is a classic uniform memory access, right? Because what we see here is the Intel Core processors, right? But they're all sharing the same memory, the same DDR3. They're not having to go through another CPU in order to be able to gain access to that memory. And this is the kind of thing that you might expect, let's say on the desktop computer, but not necessarily in a regional data center where they have very high-end servers and virtual machines running on them. So then comes this question about microarchitecture. What is that? Have you never heard of microcode? Microcode is the low-level programming that you use for the finite state machine that does the instruction register decodes, the fetch and decode. So microcode wiki. I'll just see if there's a good presentation on it. I wasn't planning on doing a microcode presentation, but it attempts to give you a layer of abstraction between the underlying hardware, the finite state machine, and the overall machine. So in the case of, I think it was the 68,000 at first was the microprocessor that had microcode programming to get symmetric instructions. You would have to program the microcode in such a way that you had like this little ROM that was inside of the CPU governing how it would behave. Let me see if these guys have a good picture. No, they do not. But if you can imagine, there's a finite state machine inside of the CPU. The microcode allows that finite state machine to change its behavior so it can have new instructions. I was hoping to see a nice picture, but they don't show you pictures, which is too bad. How about if you do images? Not seeing good pictures of there either. Oh well. Usually I like to start with a nice picture. There's a microarchitecture. So let's see if we can figure this out. There's the microcode right there. Ooh, he got big. And you could see he's helping the decoding of instruction registers. And so what's going on in here is if you wanted to add an instruction to the CPU, you could rewrite the microcode. Think of it like the firmware of the CPU. And then that actually takes the form of silicon. That would be coded into the chip itself. And then in principle, it would help with the decoding after the instructions are fetched. So typically what you do is you do an instruction fetch, an instruction decode, an instruction execute, and then a data store. Well, if you want to add instructions on what kinds of instructions you can execute, it is added in microcode. And so the microcode architecture gives you that flexibility. Let me see if I can zoom out here. Oddly enough, I cannot. Seems like there should be a good way to do that. Let's see what else we got in here. Cache, decoders, buffers. Multiple ALUs. Have floating point division, floating point multiply, dual port RAM, and a translate look-aside buffer, and a shared bus. That shared bus, oh boy, I shouldn't have clicked. I'll go out again. That shared bus is going to be shared by other CPUs in order for them to gain access to the main memory. That would be like the DIMMs and that stuff. So is the Intel Core microarchitecture a multi-core architecture? What do you think of that? Well, we know they have multiple cores, right? So it must be. It must be. Intel, I think they now measure the performance in terms of how many cores they have or something like this. That's how their marketing works. They advertise cores. They have 8, 10 cores, maybe more now. Actually, they have probably more. So we see Intel Core processors differ in the socket use, bus speed, and power consumption. So what kind of processors have we seen with i9, i3, i7, and they changed, right, the number of cores even as time progressed. So everything was changed, speed, socket, and power consumption as you went from one Intel flavor to the next. In other words, if I say I have an i3 from today, that could be as fast as, let's say, an i7 from 3 years ago. So the actual term i3 through i whatever 9, I guess it is, doesn't necessarily indicate performance, especially with relation to prior generations. This is the interesting thing when you look at YouTube videos about performance of the M1 Power book, right? Because that's shipping now and people have started to get it in and they're running benchmarks. And what do? They compare it against last year's Intel-based Power book. Well, that's not a fair comparison, right? Because now you're dealing with something that's at least a year old, maybe 2 years old. In other words, a whole generation old, because these guys are doubling in speed doubling transistor appetite at least every 2 years. So comparing an Intel MacBook against an M1 MacBook, it doesn't feel like a correct comparison to me. Even worse, often they don't even tell you what is inside the Intel MacBook, which is really critical. So it's quite likely that it's an i3 from last year, which means it was like a 2-year-old design, at least. And so I kind of question those comparisons, even though they do make the M1 look great. There's no question that it looks terrific in terms of speed and such. But I don't want to be an early adopter on that one because who knows what kinds of bugs you'll find. And they're already finding bugs. But that's normal, right? Brand new architecture, just coming out, bound to have some issues. Bound to have issues. Core microarchitecture provides more efficient decoding, execution stays, caches, and buses, reducing power consumption of Core 2 branded CPUs while increasing their processing capacity. This is sounding more and more like market speech, but do you think that's true? Any ideas? We know what caches are, know what buses are. Do I have to call on people? Angelica, what do you think?
Sorry, which question are we looking at? 12 or
13.
13?
13.
13 is true.
True. That is correct. That is correct. All right. So here's an interesting picture. This is the Core 2 architecture. Uses microcode and a microcode layer of hardware level instructions that implement high-level machine code instructions or internal state machine sequencing and many digital processing elements. I think we kind of looked at that already. There's the microcode right in there. And that, in fact, looks like the picture we were just looking at. And that is true. Also true. These are the, you can see in here, SSE. Those are the system SIMD extensions. So the SIMD extensions are the ones that allow you to do single instruction, multiple data. And so what that'll do is it'll say, let's multiply this vector of numbers against this other vector of numbers. And so that allows you to do several multiplies at once, or several adds and multiplies at once. So now we want to know about the number of cores, cache size, and socket types enabled. Enables characterization of the core CPUs from Intel. Enables, what does it enable? Enables characterization of the core CPUs from Intel. Sure, why not, right? Because why? If I had anything to measure a CPU by, if I'm going to, let's say I'm one of those crazy people who buys like a multi-$1,000 chip for my regional data center. How do I know what's in the chip? And the answer is, well, there's cache size, number of cores, maybe knowing that I can plug it into my motherboard, the socket type. These are the things that help me to characterize the chip. So speaking of socket type, the next question, this is the land grid array, LGA 775, known as a T-socket. Now, here's the interesting thing, and this is a question of what is the best way to design a chip that has this many pins. First, this here is 775 contacts. Right, so this is one big honking field of little tiny springs. Little tiny springs. And what you do is you lay down your ball grid array on top of the little tiny springs and you press fit this overlay on top of the back of the chip. Then you take one of these little levers and you swing them down and it holds the chip and the little overlay in place. Now, let's assume for a moment that you have big fat fingers and you touch one of these springs and you bend it. You are screwed because you've just wrecked your motherboard. So you don't touch that. Now, in comparison, AMD has taken a different approach. What they did is instead of putting a ball grid array on the underside of their CPUs, they put a 775 pins sticking out. And if you bent a pin, you could bend it back. And then they had a receptacle for the multi-hundred pin chips. And it was also a 0 and first insertion force socket, which meant you could drop it in and then swing in a piece of metal in order to hold it in place. What do you suppose that is over there, those little can thingies? Arduinos have these too, you know. Someone asked me what it was. I had to look it up. Anybody know? That is a surface mount electrolytic capacitor. Surface mount so you can do wave soldering or whatever, reflow soldering when you go to production. Surface mount. I've got a bunch of them right in here. They're probably using them to buffer the power supplies into this big chip, which is, I'm sure, piggish when it comes to power. So now comes the land grid array with 1,156 pins, known as socket H. This is why it's so important when you go to buy a CPU that you make sure it fits into your motherboard, or else I think bad things will happen. So it says here, H1 is an Intel desktop CPU socket. And that sounds all reasonable to me, so I would give that a true. And I'm just telling you this stuff so you can get familiar with some of the ideas, involving these different chips. They're huge. I mean, if I had to wire up 1,156 pins, forget about it. That's why they have printed circuit boards. I couldn't do it. I'd make a mistake. Probably blow out the whole thing. So then there's this question about the North Bridge. What happened to these LGA 1156 processors? And the answer is they got big. And what did they do with their bigness? Well, they incorporated more of the ancillary CPU chips, the support chips for that family. So the North Bridge got incorporated into the 1156. But then the question is, okay, so what's a North Bridge? Right? How does that work? North Bridge. So there's North Bridge and there's South Bridge. South Bridge is for the slow stuff. ISA, USB, PCI, IDE, by buoy, legacy, all that South Bridge stuff. North Bridge is the other side of the railroad tracks. That's where the CPU is at. It's got a front side bus, a little RAM, and a PCI Express slot. So North Bridge has to run faster, and it has to be closer to the CPU. South Bridge probably has some buffer in it. So if North Bridge says, okay, I want you to write this data out to the USB, South Bridge can handle it because it has a lot of buffer, and it can free up North Bridge from having to deal with it after a blind data transfer to South Bridge. And certainly we don't want to bug the CPU if we can avoid it. Any questions about North Bridge and South Bridge? So according to this, the 1156 processor incorporates the North Bridge chip into the CPU. It's a natural evolution to continue to absorb more functionality into the primary processor. Anybody out there try doing some overclocking? Is everybody familiar with the process overclocking? Avery, do you know what overclocking is?
I don't.
Okay. So with overclocking, what we do is we try and get the CPU to run at a faster speed. Oftentimes it gets hotter and needs more power. As a result, what we'll do is we'll add heat sinks, or we'll run the thing under some very hard to heat up material, such as I want to say baby oil, but it's not baby oil. It's mineral oil, unscented baby oil. And the mineral oil, when in its pure form, will allow non-conductivity and good heat conductivity. So it's electrically insulating, but thermally conductive. And as a result, it conducts the heat away from the CPU and allows you to heat up the fluid, which takes a long time because it has a high specific heat. I used to run a computer under mineral oil, which I would buy from the restaurant supply house. And that mineral oil was in a fish tank, and I'd put the whole motherboard in the fish tank. And even the power supply can go in the fish tank. The fan still turns, but it turns really slowly. And it doesn't do anything, except it looks cool. And so you can start to overclock and things will heat up a little bit, but not so much that you would notice it, except over maybe a long period of time. In fact, you can electrically push devices beyond their specifications and hold them there if you provide sufficient cooling. So if you take a little LM309, what do they call this? LM305. Let's see, that's a linear regulator. They're good for about an ampere. That's one. See this regulator? He's got a metal tab, and that metal tab is designed specifically to be hooked to a heat sink. And you want to use a little thermal compound in order to be able to keep this thing cool. Well, as it happens, if you can keep it sufficiently cool, you can run the temperature well in excess of an amp. So I was running it underwater and cranked the voltage, the current draw to a couple or 3 amps. And then the thermal gradient became too great between the die and the outside case. So it fractured and went off like a depth charge. It was cool. And you can do a lot with this kind of electronics if you cool it properly. So here's North Bridge and South Bridge again. North Bridge connects to the CPU, and South Bridge. It is designed to be high speed. Yeah, relative to South Bridge. Let's take a look at the next one. So here's PCI Express. And it defines speed for a certain number of channels or lanes, as they like to call it. And these are gigatransfers per second. But it all comes down to gigabytes per second. And here's the interesting thing, 63 gigabytes per second times 16. So that's pretty cool. So the answer to that is also true. And here we are again looking at North Bridge and South Bridge. A South Bridge chipset handled all the computer I/O functions, blah, 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 and the IDE channels. Also true. And you could see that here. And here is South Bridge is slow for interfaces like USB and parallel ports. And that's essentially true as well. You could say that's why it's slow. Since we're dealing with I/O and we're I/O bound, we want to be able to offload from the CPU those transfers. So we do what's called direct memory access, and we allow the South Bridge to have direct memory access to the memory, the main memory of the CPU. So DMA is a feature of computer systems that allows certain hardware subsystems to access main memory, independent of the central processing unit. Yes, that's true. And that's why we want South Bridge as an I/O controller to have DMA access to this memory here, because we don't want to have to bug the CPU to do a data transfer. South Bridge ought to be able to handle that for us. So now we're back to the LGA1156. I'm not even sure that's the biggest socket they have. There's probably something larger now. So now, are all LGA 1156 processors and motherboards interchangeable? Can I swap a Celeron for a Pentium or a Core 5 with integrated graphics? Or an i7 without graphics? Does that seem reasonable? Beatrice? Beatrice Guevara. How about Caroline Nelson? Caroline, are you there?
Yeah, sorry, I thought I was unmuted, but I was muted.
Oh, yeah.
4 is true.
24 is true. That's correct. Let's do 25. Now here comes a bigger one. All right. The LGA2066, also called socket R4, is used in Core i9. Anybody have an opinion about that one? Daphne, what do you think?
I'm not sure. I think. No, I'm not sure.
Okay, the answer is yes. You can always look these things up if you're interested enough to want to know more about this stuff. Whenever you go shopping for a computer, if you're going to be building it yourself, you're going to need to know that the CPU you buy for that computer is going to fit. And here it is. It's called socket R4. Another land grid array with a whole bunch of springs. I've actually messed this stuff up pretty good and tried to fix it with tweezers and a microscope. It is tough. It is tough. These things are tiny. This guy didn't even make it so it was clear. It looks a little blurry to me. But this is not easy stuff to fix once you touch it. But at least it's, by bending these instead of, let's say, bending a pin, maybe you save the chip. I don't know. Those chips can be rather expensive. Let's see what they've got here. Yeah, there's a bunch of interesting Core i9s available and even some Xenons. And look at the price of some of these chips, $2,500. Way to go. And that's just the chip, right? That's nothing else. That's just the chip. And that's from 2017. So it's already 3 years old. So what is the largest socket Intel makes? I don't even know. I used to know. Oh boy. 3,647 pins. What a monster. I don't know. There's got to be a better way. Can't they do this with fiber optics or something? What are the limits? It's not even an integral power of 2. They at least should have had the decency to stop at 32,768 or something. That's a lot of pins. So here comes Core i9. And look at all the cores, 18 cores. Does that sound right? Let's try and call somebody. Eric. E-R-I-C-K. Eric, are you there?
Yeah, I'm here.
So what do you think about this Core i9? Does that go up to 18 cores?
Yeah, that's true.
Cool. Cool. let's see, 27. The Core i9 consumes 140 watts. Is that always true? Let's see who we can ask. Harshal, what do you think? Is that always true?
Not sure.
Yeah, so the answer is no. Some of them consume only 120 watts. And in fact, I think there are probably new ones out that can consume even more. So here's a question. Can you find Core i9s that use DDR4 RAM? Let's see who we can ask on that one. Jacob. Jacob Cassidy? Not here. John Fee.
Yeah, it's true.
That is true. It is true. Let's look at 29. Oh no, we just did that. 30. We're getting through this, but how many questions are there? There's a lot of questions. It says here, synchronous dynamic random access memory, or SDRAM, is any dynamic random access memory where the operation of its external pin interface is coordinated by an externally supplied clock. Let's see if we can find somebody. Jorge, what do you think of that? Does that look true? Jorge
That the operation of its external pin interface is coordinated. I think that's true.
It is true. Yeah, you need an external clock to make it synchronous. So here's this interesting thing called quad data rate RAM. This is when you're quad banding the RAM with 4 channels. Quad data rate RAM has 4 signals per clock cycle by delaying the clock by 90 degrees. And so here you can see where he strobes the RAM. So 4 signals per clock cycle. Quad data rate. 4 signals per clock cycle. Does that sound true? Let's see who we can go to. Kristen.
Yes.
Yep, that is true. That is true. Here's another one. Standard transfer rates are 1600, 1866, 2133, 2400, 2666, 2933, and 3200 mega transfers per second. Thus, DDR4 2666 refers to the 4th generation RAM that is SDRAM with 2.666 giga transfers per second. True or false? Lamb.
I think it's true.
Also true. Also true. So we're getting exposed to an awful lot of nomenclature here. A lot of sort of interesting ideas about speed and such for RAM. So here's this thing called fabless manufacturing, the design and sale of hardware devices and semiconductor chips while outsourcing the fabrication. Let's see, who hasn't gone yet? Ricky. What do you think? True or false, Ricky?
Yep, that's true.
Also true. So what would be an example of a fabless manufacturer, Ricky?
Anyone that outsources to Taiwan Semiconductors, I think
That's right.
AMD, is that right?
That's right. That's exactly right. NVIDIA, Apple, not Intel. Intel used to outsource their Atom processors. I don't know what they outsource to them anymore, if anything. So AMD is fabless, just as you said, and it's just like ARM. And in fact, NVIDIA bought ARM recently, and the stock is taken off like a rocket ship. I'm afraid I missed that one. Oh well. So here's the AMD 9080, a reverse engineered clone of the Intel 8080. Does that sound true? Let's Shamrock. What do you think? Is that true?
That sounds false. Aren't AMD and Intel two separate companies?
Yeah, they
So
are
what-
separate companies.
So wouldn't that be false?
Well, reverse engineering refers to examination of one person's product in order to create a design from it. So
So-
just because they're two different companies doesn't mean one can't reverse engineer the other and make a clone.
So it's true.
It is true. It is true. Let's see if I can bring it up. There it is. The 9080. A reverse engineered 8080. So you could probably make a compelling argument that somebody should get in trouble for stealing the design. But are they really stealing it, or are they just reverse engineering it? And if you're just reverse engineering it, maybe that's okay. In comparison, if we looked at what, for example, Motorola did, when MOS technology came out with the 6501 clone of the 6800, Motorola got very upset, and it was even plug-in compatible, and so Motorola sued them. And I have a vivid recollection of this, actually. 45 years ago. Good. Where's the time gone? So the interesting thing here is that the people who came from Motorola went and started MOS technology, and they started with a computer chip that was much, much cheaper than the 6800. And so then they came out with the 6501, and then the 6501 led to the Apple one, and then the 6502 had the Apple II, and then that basically launched Apple. I have one of these Apple IIs sitting in my attic. There it is. And you could see its mass storage device is the cassette deck, and that operated at 1200 and 2400 hertz. So you would have 1200 hertz would be like a 0, 2400 hertz would be a 1. And that's typical, when you want to encode baseband information into a broadband storage device. And we're considering cassettes to be voice grade broadband recorders. So if you were to listen to this, I don't know if I can do this. Let's see if this works. Yeah, there we go. I don't know if you can hear that, but that's my little Arduino dialing the phone. I was debugging this earlier this morning, and it was driving me crazy. So basically, that's a way to encode a series of symbols into tones. That's called a dual tone multiple frequency system, or touch tone system. And if you have a way to record it, effectively you're recording data directly onto some sort of audio media. So that's a broadband modulation of a baseband technology. The Kansas City standard used to run much faster than the touch tones that you were hearing, because you can hear distinct touch tones there. But in fact, you can play them much, much quicker if you like. Just people won't be able to understand them, and neither will the phone system. So I think we're up to question. I hope I didn't lose my place here. It looks like I did. I think we were up to question number 35. And that was homework number 11. So now comes the next question about the front side bus. A computer communication interface. A front side bus is a computer communication interface. Let's see who we can call on next. Stephanie.
I think that's true.
Yes, that is also true. So it looks like we were able to call on everyone today. That was good. How many more questions are there? We're up to question 37 now. Jeez, this thing goes on and on. Who makes up such long tests? This is terrible. They ought to get that guy, whoever he is. All right, so I don't know. I have trouble with market speak. Hyper transport, formerly known as the lightning data transport. Lightning data transport. Where do they get these names? A technology for interconnection of computer processors. Bidirectional, high-speed, parallel, low latency, point-to-point link from 2001. 26 gigabytes per second. I got to get my calculator out for this one. 26 times 8 is 208 gigabits per second. Well, that sounds pretty fast. Does that sound true to people? What is this hyper transport anyway? Can I buy one? I'm thinking this is kind of like the Hyperloop, right? Whizzes you from one place to another. So there it is, non-uniform memory access. So there's memory over here and there's memory over there. And if socket 1 wants to reach the memory over next to socket 2, it's got to communicate through 2 processors to get there. That's going to slow things up quite a bit. And this is communicating through the hyper transport. So this could be right on the motherboard. Here's another one. Yes, they're using Northbridge to communicate with one another. And then if I want to get from here to there, I got to go through 2 North bridges to get to the DRAM. So it's not uniform transport. This is hyper transport. So hyper transport is an example of NUMA, non-uniform memory access. Looks like to me. Let's see if we can get back to where we were. Hyper transport. So, wow. I think we're all getting a little burned out on this. Let's take a break. So this is, we're up to question 37. I'm going to make a note on my calendar, and we will pick this up, this coverage, when we come back, which will be on the 30th. So let's do that. We'll do homework 11, and we'll start off on question 30. Seven, 37. Because even I can't go over all this all at once. It's just too painful. Wow. Instead, let's try something a little bit different. So we already took a look at the NUMA overview, NUMA architecture. And we know a little bit more now about parallel architectures. We've seen issues about hardware and its integration with RAM. I think what happened was we examined initially the so-called Flynn taxonomy, SISD, SIMD, MISD, MIMD, but we didn't really talk too much about how RAM is handled as a system. And I also, I think, mentioned how you could refactor some of the code that we were looking at. And we went from for loop splitting to forms of data parallelism that looked like SIMD type parallelism, where you could take chunks of arrays and arrange them in strips. They call it strip mining. When we started looking at the SIMD type ALUs, we were really looking at vector coprocessors. A vector processing unit required that you have a homogeneous array of numbers and an operation that would perform between two homogeneous arrays. So you could add and subtract, or here we have adding 10 numbers together to get 10 numbers as a result. And they call that vectorization, fancy name for simple idea. It's very typical for academics to have fancy names for simple ideas. We like the vectorization because vectorizing compilers exist and they can exploit the vectorization. They can exploit vector capabilities in the hardware, and that's important. But it's good for homogeneous data structures, which means arrays. You have to have a vector. If you don't have that, it doesn't work very well. And then there's the graphics processing units. Now, these often have vector processing units inside of them, but they also have multiple cores. And MIMD is a little bit closer to what I see in GPUs now. It's multiple instructions with multiple data. And with that sort of thing, you're able to take advantage of many CPUs. And it's almost as though you have a multi-core system. You have a multi-CUDA core system, but they're limited. Then in comes Intel and AMD with non-uniform memory access multi-core systems where the chip has multiple cores and there's multiple chips on a single motherboard, but then each one has its own local memory. And in order for one to get access to the other one, you have to jump through hoops, go through another intermediate CPU. So this is a little bit closer to the way I envision the M1. I mean, believe it or not, it looks like a uniform memory access computer because all the CPUs go through the same switching fabric in order to get to the memory. So that seems quite uniform to me. And that's something that we don't normally see for the larger computers. But for a laptop, I see no problem with it. But the interesting thing about it is some of those things aren't really CPUs. They're neural engines, or they're, I don't know what else they had. I forget now. Other things. Oh, right. They had the low energy CPUs, the fast CPUs. They had a couple other block diagrams in there, including a processor for images. Image processing really does lend itself to vectorization. And that's because you're dealing with an array of pixels. Well, if you've got an array of anything uniform, like a scalar data type, like ints, well, then you're gold. That's the kind of thing vectorization works well on. So here's what AMD came out with. This is called the bulldozer. The bulldozer. So Here's an instruction decoder, more cache, a floating point unit, a integer computation facility, a dispatcher, core instruction fetch, more cache. Every CPU core gets its own L1 cache. And then there's the so-called shared L3 cache. And what you want to do is you want to try and see if you can gain access to the memory you want by finding it in L1 cache. If you don't find it there, it generates a cache miss. So now things are going to get slower. So you go to the L2 cache, which is rather larger, but the performance is decreased. And then you generate another cache miss. And so then you go to the L3 cache, where things are slower still, and it's shared. And now you've got, after that, to go out to DDR memory. So if you're looking for an address with some data in it, and it's not in any of your caches, it generates a sequence of cache misses. And that's handled by the memory coprocessor or memory controller. Whoops. So now here we have the NUMA in the multi-core system, and this is actually something which you can see on the motherboard. You'll see a series of DIMM slots surrounding one chip, and then another series of DIMM slots surrounding the other chip. And in general, what will happen is you'll want to try and confine the program that runs in chip 1 to the memory directly connected to chip 1. And so then the interconnect enables us to have access to memory from one CPU to the other. And if we have a homogeneous collection of CPUs, in principle, they can eventually share each other's memory and accelerate one another. And this is the kind of system you might find in the rack in a regional data center. So if I think about the M1 CPU, I think about a shared memory interconnect, right? Everybody has to go through the fabric in order to get to the memory. Whereas if I think about this kind of a CPU, I have a distributed memory interconnect. Every CPU gets its own geographically co-located memory. So here's a, I don't know, kind of an interesting variant. Instead of going through switching fabric, we'll go through the bus in order to get to the memory. And that's a problem, right? Because if we're all going to share the same bus, if it's not a switching fabric, somebody has to have ownership of the bus. And then that ownership allows this processor to gain access to all that memory and read the memory in and write answers back. And then once it lets go of the bus, the next processor can run. But without the abilities of being able to communicate without dominating the bus, you essentially cause a contention problem, right? This causes thrashing. The problem is this processor can make no progress if it doesn't have access to memory. And the processors go blazingly fast, but if their access to the memory is blocked, then their throughput falls precipitously. And now here comes the crossbar switch, which is what I think they're doing with the M1 computer. And so that gives you a kind of compare and contrast between, the modern M1 computer and some of the older bus architectures. The cross-point switch is interesting. If you have a switch matrix, right, and you want to determine which switch is being depressed, right? In other words, reverse the problem. Use this as a keypad. Every intersection has a switch. One switch is pressed. How do I know which one is pressed? Well, you add power here, and then maybe you add power there, and then you start measuring along here. And if you can find the power from here coming out to there, then you know where it's pressed. And you can sequence through here and this one and that one, power each one in turn and figure out what row you're on. Then go through in this direction and figure out what column you're on. And in principle, you'll get power from only one place. So let's see what else there is in here. Okay, here's something you don't see every day, but it did exist as a high-speed computer. The toroidal topology for communication is not being drawn here properly. But if you look at the Cray T3D, you'll see it's a computer that kind of looks like a donut where the CPUs are sprinkles on top of the frosting. I know that sounds like a mixed metaphor for something or other. But if you look at Digital Equipment Corporation's Alpha chip, which is a RISC chip, they use that for the Cray T3D, which is a donut topology computer. Let's see if they give you a picture. They do not. There it is. This was regarded as a supercomputer in its day. Donut topology. It's a 3D torus. And so then this isn't even looking like the torus that I would like to show you. But in fact, if you wanted to visualize this like the donut with the sprinkles, that's what that would look like. I wonder if they give you a better picture. Maybe if I just wrote toroidal. And of course, I spelt it wrong. That looks like a better picture. Now you can kind of see how things wrap around. This should actually be more evenly distributed. So the whole thing involved passing messages from one place to another. I've often thought that adding a whole bunch of computers into a box is not a good idea, because the tricky bit has always been to program them, and that's never been easy. So this toroidal topology, that existed. There's another topology that's similar, and it was called the Intel Hypercube. And that looked an awful lot like, well, one of the K-maps drawn in 3D. And that was out in the mid-'80s. The fellows in my building had one. It's called the Mark IV. Let's get a picture. I respond better to these visual things. Yep. So this is just like what you might do with a K-map with 5 variables. Oh, here it is. That's it. 5 variable K-map right there. So once again, to go from here to there, you still have to go through intermediate nodes. And so there's a substantial penalty involved in internode communications. And there's no avoiding that. So this is sort of a bandwidth thing. When you're doing the internode communications, like this hyper transport stuff and the so-called front side bus, you end up basically doing a study in networking. And that study in networking involves things like latency and overall data throughput. And I'm not going to get into this bisection thing right now because I think it's too much. It's a little overwhelming. I wanted to take a break from going through sort of the coverage of this very long homework because we got up to question 37, and I said, man, I got to stop because it's going on and on. Let me ask you this. I'm going to stop for a second and leave a few minutes for questions. Does anybody have any questions that they want to see, pressing questions that they'd like to see answered for homework 11? I'm just trying to anticipate if there's anything in particular. So it's very much a systems oriented type of question and answer thing. So that's, I'm just going to sort of thumb through this. If you don't have any more questions about this that are specific, we'll cover the rest of it when you come back. I hope you guys have a good break. Stay safe, and see if you can't take a look at the homework 11 and bring your questions with you next time, which will be on the 30th.
Thank you.
Thank
Have
you.
a nice break.
You too. Have a good break.
Thank you.